using Python to solve chemistry equations. That's the next project in our competition. Max Gold from St. George International School will now take the floor. Good luck.
Hello, my name is Max Gold. I'm currently studying IGCSEs at St. George's International School, and I'd like to present my findings from solving chemistry equations using Python. So there are three aspects to the code which I've created. First of all is an element and compound dictionary, which stores the values of elements and compounds that are relevant in solving these chemistry equations. Balancing chemical equations, which is a prominent problem in our GCSE chemistry courses, which makes sure the number of products and reactants on either side of a chemistry equation are equal. And finally, it's using compound formulae with the valency manipulation. So trying to find the simplest possible formation between any permutation of element or compound. So firstly, before you can begin computing balancing equations or using valency, I thought it would be quite important to have a database full of elements and compounds to make it a lot simpler to use to retrieve information for this program. So it stores vital information about elements and compounds. It's very easy to use because each database has a key, and that key is the element itself, the hydrogen, for example. And each key has specific generic fields of data to be stored, such as its electron structure, valency number, symbol, and these are the same for every single element, making it very easy to obtain information. It saves a lot of time of having to manually input data, such as with valency. Having to manually input the valency can be quite difficult and quite time-consuming, and so being able to retrieve this information from the database is very useful. It also formats formulae preemptively using a translate function, which allows symbols with numbers inside it to appear with subscript. And it's the main hub for all my other programs of balancing and valency manipulation to gather the data. Here is an example of the database for the elements. As you can see, the keys, such as hydrogen, helium, and lithium, they all have the same generic fields, making it very easy to look at data. And we have the same here for compounds, which we use in GCSE chemistry. Now, balancing chemical equations. This is basically to make sure that that equalizes the number of products and reactants in the chemical equation in order to follow laws of conservation of mass, as well as being able to know quantities of elements using molar mass, which can come along in the future. It uses Gaussian Jordan matrix elimination in order to balance the matrix of elements to make sure that you get the right coefficients for balancing the equation. Used for calculating compounds, like I've said, quantities with molar mass, and it follows the law of conservation of mass. This is an example of Gaussian Jordan elimination, which is the aim to convert a matrix into basic ones and zeros. So this is the first bit of the code, which separates the elements into a matrix by taking the number of elements per compound, per product, and per reactant, and that forms an overall matrix, which can be used in this Gaussian Jordan elimination function. Again, this is further proof of using brackets, like the number of elements within brackets. It can multiply the certain number of elements depending on the number outside of a bracket or inside of a bracket. I have some examples on my laptop which I can show during the questioning time. Row echelon form, also known as Gaussian elimination, uses three matrix operations in order to begin to balance the equation, as you can see up here. So there's row switching, which involves switching the two rows together in order to produce ones and zeros. Row multiplying by a coefficient. So imagine the first number was 3, multiplying by a third would return a 1. And multiplying one row and adding it into another in order to cancel them out, producing zeros. This process goes from left to right, top to bottom. This is an example of multiplying one row and adding it to another, and that's the general formula at the top. Now this is how it's coded in Python, and as you can see, there are all three matrix operations, which you can use. It detects whether the number is a 1 or a 0 or any other number, and applies these rules in order to balance it. Now, to further balance the matrix, we use reduced row echelon form, whose full name is Gaussian Jordan elimination. And this provides ones in a diagonal line with zeros on either side. And the final row, or the final column, sorry, is the coefficients that are used to balance the equation. It balances the entire matrix. It changes the stars originally from row echelon form to zeros, just to perfectly balance it. And it does the opposite of what regular row echelon form does. It goes from right to left, down to top. And this is it's much simpler because it's already dealing with much fewer data. So yes, this is an example of reduced row echelon form. And in order to finally get the coefficients, you take the last column, as I've said, and these will provide the coefficients for each of the compounds in an equation. They're also converted to integers because Python doesn't really like to deal with floating point numbers, so converting it to integers is a lot easier. The final element of my program is valency manipulation. Now, this creates the simplest possible compound between any two elements, any two compounds, or an element on a compound, any permutation that's desired. It's adaptable in the code. It's useful for GCSE revision that we do because I know there are a lot of students in my school who struggle with the concept of this valency manipulation, and so this can give them an insight as to how it really works. And this is the method that we use at GCSE. It's called the swap and drop method. And it takes the valences, which is the willingness of an element to react with something else. So for example, nitrogen's valence is 3 and hydrogen's valence is 1. The swap and drop method swaps the two valencies around, simplifies them. If it cannot be simplified, then it leaves it as it is. And so the final formula for the combination of nitrogen and hydrogen would be NH3, as seen by the swapped coefficients. Now, this is the collection. The left-hand side is the input of the elements. And then what the computer does is it looks at the database, retrieves the valency, and then on the right-hand side, it does the swap and drop method. And then finally, at the very bottom, it assembles it. Another good thing about the balancing function is that it can be used in these valency equations as well, balancing these simplest formula combinations. Thank you for watching.